Good morning, everyone, and it's time to start. Right. It's only the second class, right, because of that holiday, right. So we missed one class, and as a result, we're still in the electric field. So today, the whole class, we're going to talk about the electric field. And again, as usual, guys, right, if something not clear, say something, right, and I will clarify it. Or just in terms of just a handwriting, if something is not clear, tell me. Okay, so let's introduce first a short review about the electric field, and then a few problems as usual, right? Right. So let's assume that we have some charge. Let me put it here. Q capital. It's a charged object, so of course it creates an electrical aura, right? Electrical aura sounds mysterious, right? So researchers gave a cool name, the electric field. So it creates an electric field. So the question, how can we measure, how can we introduce, define, and measure that electric field? So we agreed that in the cases like this, we use a probe charge. And that probe charge, okay, we can position, for example, we're interested, let's say, at the electric field at this point. So we take Q probe, right, at a distance r, for example. Let's say we want to measure the electric field at that point. And of course, we impose restrictions on this Q probe. Q probe first must be positive, and the second must be small, right? Positive so that we will have the same direction, small so that we would not destroy the system, electric field of which we want to measure, right? And then what we do, we measure the electric force acting on the probe charge F, right? And then divide it by the value of the probe charge. So that's how we introduce the electric field. So as a result, electric field, by definition, it's the force acting on the probe charge divided by the value of the probe charge. So that's how we introduce the electric field. Right. And units, there are no special units. For me, it's kind of unfair because electric field is one of the fundamental quantities in physics overall. Like electric field, magnetic field, very, very important. But it's not a big deal. The units of electric field, just whatever you see in the formula, newtons divided by coulombs. Newtons divided by coulombs. Then, of course, for this particular case, if an electric field is created by a point charge, we derive the formula. Right? So, electric field for a point charge, it's a K, that universal constant, times Q, the source, divided by the R squared. So that is the electric field of a point charge. Right. Okay, so let's frame it because it's a formula which we are going to use from time to time, or even more often than from time to time. We will use it often. Right. So again, this is general definition. You can apply it to find the electric field of any system. This formula is only for a point charge, so we have to make that clear. Right? Then another thing, electric field is invisible, right? And of course, it's very, very inconvenient. So we usually come up with some tools which can be used to visualize the electric field so that we can draw something. Okay, we decided to use what is called the electric field lines, right? All right, and let's say that, okay, let me write over here, the electric field lines, right? So we use them to visualize the electric field. And let me draw some arbitrary set of electric field lines. Let's say over here. Let's say these are my electric field lines. But of course, and yeah, when you see the electric field lines, you can get information about the electric field quickly, where the electric field is stronger, where it is weaker, and information about the direction of the electric field. So every time we're interested in two pieces of information: direction and the strength. Because the electric field is a vector, so it has two components, two parts, magnitude and direction. So first, how can we get, for example, direction of the electric field at any point? Let's assume at this point we want to know the direction of the electric field. Again, these are just electric field lines. They're useful auxiliary lines. But still, we need to know information about the electric field itself. Okay, so direction, all the time tangent to the electric field lines. Okay, it's probably too long. Let me make it shorter. Okay, but anyway, it's tangent. Or at this point, for example, what's the direction of the electric field? Tangent. Right. Or over here, I will draw it in a second. Then, information about the strength is in the density of lines. Here, density of lines smaller, so the electric field must be weaker relative to the points over here. So here, density of lines is larger, so the electric field must be stronger. So if you draw a vector, it must be longer. Right? So that's why I stopped. That's why I didn't finish this vector. Right? So over here, I can draw this is E, electric field at this particular point. This will be electric field at this particular point. And if I want to draw it here, density of lines larger, so the electric field vector must be longer. So that will be electric field at this point, or for example, at this point. Again, it must be tangent, and density of lines gives you approximately the length of the vector. Okay, so that's how we should read the electric field lines. And of course, for the simplest possible cases, let's assume that if you have a positive charge, which creates an electric field, then electric field lines are straight lines and pointing out, sort of like this, right? It's a consequence of the fact that we decided to use positive probe charge, right? So the electric field lines, all the time, they start on positive charges. If we, for example, look at these electric field lines, it means what we can get from here. It means that somewhere over here, there are a bunch of positive charges. And somewhere over here, a bunch of negative charges, because you see electric field lines go that way, and you remember they end on negative charges all the time. So, and if we here, let's say we have a negative charge, which creates an electric field, right? So then, of course, electric field lines will be towards. Right. Again, you must understand that this is separate system, this is separate system, and this is separate system, right? They're not connected. Right, okay, so that's what I wanted to say about the electric field lines. And what's next? Another very important formula, which is one of the fundamental, electric force, right? Electric force. Now, the electric, every time I make a mess over here, electric force. So if you have, for example, some electric field lines, right? Let's say this is electric field. And let's say you have some charge, Q, which is exposed to that electric field. Of course, that charge is going to interact with the electric field. Just God created nature this way, they interact, right? And we can find the value of the force by just multiplying charge and the electric field, the value of the electric field at the point where the charge is. Basically, just solve this formula for F. F will be equal Q times E, right? So force, electric force equals Q times E, right? So it's one of the most important formulas. Again, closer to the end of the semester, this formula will be added to the set of Maxwell's equations. We will have set of Maxwell's equations, fundamental equations, and this electric force with the magnetic force will be added. Right? And of course, direction of the force depends on the sign of the charge. So be careful, right? So if charge is negative, then direction of the electric field will be flipped to give us direction of the electric force. So that's what I wanted to review. It's very simple things, right? These are very simple things. And now let's start looking at examples. All right, so this I discussed, so we can skip this. Again, guys, if something not clear, just say something. 23.3 problem. So it's a chapter 23 and problem 3. Two charges, two charges. And very similar problem will be in your homework. You know what? Two charges, and we will have to find the electric field at a certain point, net electric field. Let me start with the picture. Then it's easier to describe the situation, describe the problem. And I will start with the coordinate system. Probably yes. Right. And I will draw it here. I'm just trying to estimate the amount of space I might need. So let's say this is my y-axis. This is my x, right? And two charges, as I said, one is positive, one is negative. Let's say here we have a positive charge plus, right? And over here, right underneath, there will be negative charge, minus. Q1 and Q2, so this is Q1 of 3 nanocoulombs, I think nanocoulombs, so Q1. And this will be, of course, Q2. This is minus 3 nanocoulombs. Okay, so that's the electrical part. Now let's add some geometry. Which parts? Okay, so this distance from this point to this point, this distance is, where should I draw it? Probably here underneath. So A, this distance A from this point to that point is 5 centimeters. Right, and this distance B, also 5 centimeters. And over here also B, from this point to that point. So lots of symmetry. So that's what we know about geometry and physics. Physics is quite simple. Positive charge creates its own electric field, so the whole space is filled with the electric field created by a positive charge. Negative charge does the same, independently from each other, right? So at any point in space, if you take this point, of course, we are going to have two fields, so superposition of two fields, so we have to take care of that. But the problem asks, find the electric field at the origin. So we will have to find net electric field at the origin. So this is point O, I think I know, for whatever reasons, I label it point P. Right. Yeah. So this is point P, so we need to find the electric field at P. So we need to find E at point P. And of course, this is the net electric field, right? So, which consists of two parts. Okay, effectively, this problem, okay, not effectively, from a mathematical point of view, this problem and the problem which we solved in the previous class, you remember we found the net electric force acting on one charge in the previous class. So this problem and that problem from the mathematical point of view, they're very similar. Because we will just need to add two vectors. That's it. All right, so again, it will be sort of like a refreshing vector algebra. But of course, now the nature of these two vectors are going to be different. There we had forces, now these are electric fields. Right? And so the procedure will be very, very similar. So again, first I will draw the picture. Okay, complete the picture. I will just draw electric field vectors, and then we will follow the same procedure. Okay, I will tell that in a few minutes. So first, this charge. Okay, let me draw a couple of auxiliary lines first. This and this, right? Or maybe this as well, right? Okay, so now this charge, you remember, it creates electric field lines, right? So it means that at point P, the electric field created by a positive charge is going to point that way along the line connecting the charge and the point P. So this will be first electric field. Let me label it as E1 because this is charge Q1. Right? Again, it's just this. Right? Then Q2. Q2 is negative, so it's this picture. So one of these electric field lines is going to give us electric field, pointing, of course, towards the negative charge. So this will be this way. So this will be our, where should I draw it? Probably over here, E2. E2. Right? And of course, the strength of this field and that field must be the same because charges are the same and the distances from this charge to the point P and from this charge to that point are the same. Let me make it the same length. Okay, I will slightly make it shorter. Okay. And so now we just need to add these two vectors up as vectors. And of course, you will end up with the net electric field pointing straight down. So that's what needs to be found, right? So that's the vector. Okay, and I can tell you what I don't like about this problem. It's too vanilla. It's too much of symmetry for me, right? I think in your homework problem, you're going to have less amount of symmetry. So as a result, I will pretend that I don't know anything about the symmetry. So I will just try to solve the problem as if we did not have any symmetry. Right? Okay, so in the procedure will be like what we had in the previous class. Can we find the strength of this vector, electric field, E1? It is created by a point charge. We can use this formula. Again, that will be just a magnitude. And then we can decompose it. We can find x component and we can find y component. So we'll have a vector presented in the component form. And then the same with E2. We can find the strength. Again, it is created by a point charge, so we can use this formula. And then again, find x component and y component. And then we have two vectors presented in component forms. We can easily add them up. That's the previous, it's your homework and the previous recitation class. Right? But now just the nature of the vectors are completely different. And I remember, like, I think a year ago, I gave on the final exam the problem about something like this, right? Students got used to adding forces, but not adding not adding electric fields, and there were quite many questions. Some of students started panicking, right? So what to do? Right. Okay, so now let's get into the details. I described what I'm going to do, right? So let's first find the magnitude, E1. And now I will move faster because now at this point you're familiar with this procedure. So magnitude of E1. E1, it will be equal K Q1 divided by R, R squared. And R, which way I label it? Let me just label R1. And that R, it's a distance from the source to the point where you want to find the electric field. So in this case, R1, it's at this distance, right? From this point to that point. And so we can easily find R1. Let me open my explanation box. R1 squared will be equal right triangle B squared plus A squared. A squared plus B squared. And of course, don't forget to convert to meters. Right? So it will be 5 times 10 to the power of minus 2 squared plus 5 times 10 to the power of minus 2 squared, right? This is 5 centimeters, 5 times 10 to the power of minus 2, and here the same. So of course we will get 2 times 5 point. Okay, let me do this way. Times 10 to the power of minus 2 squared. Okay, let me close my explanation box. Right. Okay, so now you can plug numbers, calculate, charge is given, distance we found, k you know. Right, so it will be 5400 E1, 5400 newtons per coulombs. We can calculate that easily. Then, of course, we need to find components. And in order to find components, we need to use one of the angles. This angle or that angle, right? So this or that, they're equally good, right? I would never say anything against any of those. So let me use this angle. I'm just checked my notes which angle I used. Okay, so I decided to use this angle, right? And of course, by geometry, this angle and that angle, they're vertical. So this is also theta. So we can find angle theta using this triangle P, this point, and that point, right? This triangle. So tangent theta, it will be opposite versus adjacent. Opposite side B, adjacent side A. So it will be B over A. And of course, angle you can easily calculate. 45 degrees, you could have told me from the very beginning, because lots of symmetry, right? Everything is the same, right? But again, as I said, I pretend that I don't know anything about the symmetry. So of course, in this case, the angle is 45 degrees. Okay, so components. X component, this. Y component, we need to drop the vertical line, and that will be the Y component, right? Okay, let me carefully write it down. E1x equals E1 times E1, it's this side. E1x, x component, it's that side, you see? Adjacent to the angle. So we have to use cosine function in order to find adjacent side in the right triangle, right? So times cosine of angle. And, okay, now I'll pause. And what do I have to put here? Is it a positive component or negative component? We discussed that in the previous class, and I'm sure that you can answer.
Negative component?
Of course, yeah, that must be a negative component, because again, we're not using conventional angle, we're using that angle, which is convenient but not conventional. So as a result, we have to take care of pluses and minuses manually, and the component, since the component points in the negative x direction, so we have to put minus manually, so it will be minus. Right, so you can plug numbers, and of course you will end up with minus 3818. We can keep more sig figs, right? We can round them down out at the end, right? But in preliminary steps, it's better to keep more sig figs, right? And of course, E1y will be E1 times sine theta. If we use cosine theta in that case, in this case, there must be sine, because now we're finding the opposite side. And again, that component is negative. You see, the component of this E1 in the y direction is negative, so we need to put minus. And obviously, this component is going to have the same strength, right? Minus 38, 18, 37. Sine and cosine at 45 degrees have the same values, right? 1 over square root of 2. Okay, now we're done with E1. Now exactly the same for E2. For strength, K Q2 over R2 squared. And you see now I put an absolute value because I'm finding the magnitude, right? Magnitude cannot be negative. So sign of the charge will drop, right, all the time. Right, so now again, R2, it's this distance, right? So R2 will be equal to R1. Right? Okay, let me show that R2 will be equal to R1, right? But again, because of the geometry, In the most general situation, of course, it doesn't have to be this way. Right, okay, let me emphasize, it's in our case. Right? And of course, the strength is going to be the same as the first one, 5400. So, as I said, if you calculate, of course, you will end up with the same, right? 5400. And components. Components of E2, again, we will drop these dashed lines in order to find x and y component of E2. E2x, of course, it will be E2 times. Okay, again, because of the symmetry, this angle is going to be theta also, right? But of course, in the most general situation, if there is no symmetry, of course, you will have to pick one of these angles, calculate it, and use it. But in this case, because of the symmetry, that angle is also theta. So I can recycle it. So I can use, in this case, x component can be found using sine of theta. And yes, sine. That component positive or negative? We're talking about this component, right? It points in the positive x direction, that component, so it must be positive. So I put plus. Right, and the y component, it will be E2 times cosine theta. This component, again, of E2, it points downward in the negative y direction, so that component is negative, so I have to put minus, right? And of course, it will be the same minus, 38, 18, 37 over here, both of them. But one is positive, one is negative, right? So it will be 38, 18. Okay, done. So we found components. And now we just need to add them up. Principle of superposition, right? So now E equals to E1 plus E2. Powerful principle of superposition. So it's in a vector form, but we need to add components, corresponding components, this and that. So E sub x equals to E1x plus E2x. Of course, they must cancel each other, right? And they're canceling. This is positive. This is negative. This is positive, right? And from the very beginning, we saw it because the electric field, the net electric field points straight down. So the electric x component must be 0. And E sub y, of course, it will be E1y plus E2y. Of course, we double. They add each other, both negative. So you're going to get minus 76.37 newtons per coulomb. Right. So these are components of the net vector, and of course it points downward, right? Sorry. So you see, the procedure is very, very similar to what we had in the previous class, and as a result, that's why I move a little bit faster, right? Of course, pretending that I don't know the symmetry, because in your homework there will be less symmetry, significantly less symmetry. Right? And again, so we spend so much on vector, refreshing vector algebra because we're going to use it pretty much every class in this semester. Okay, let me move to this side. Right. Okay, so let me move here. And now I need to start erasing the review. And so this problem, similar problem will be in your homework. It's problem 29. Let me erase this. So 23, 29. All right, and yeah, sometimes I give similar problems on the first midterm exam. So what do we have here? first of all, we have a system which we haven't introduced in our lecture. I'm going to do it tomorrow. So the system is this. So what if you have a infinitely large surface? For example, this wall charged uniformly with charge. And charge density, surface charge density, which we discussed in the previous lecture, is given. That system, infinitely large charged surface, gives us a uniform electric field. And tomorrow we will introduce the expression for the electric field created by that surface, right? So we're going to use, so let's assume that we have a surface like that, negatively charged. Okay, maybe I will start drawing. All right, so let's assume that this is my infinitely large, negatively charged surface. Minus, 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 right? So large surface with surface charge density eta, Greek letter eta. It's sort of like an N with a long tail down. Greek letter eta. It's a negative minus 2 times 10 to the power of, minus 6 units. You remember how we usually find, how can we find surface charge density? If you know charge, right, total charge on the surface, you take the charge divided by the total surface, that will be surface charge density. So it should be coulombs divided by square meters. So it will be coulombs divided by meters to the power of 2. Right? So these are units. Then what else is given? Before I introduce the second player in this game, so as I said, this system gives us a uniform electric field. So it means that I can draw, and again, you still remember that electric field lines, they start on positive charges and on negative charges. In this case, we have only negative charges. So just electric field lines are going to do this, right? So these are, okay, let me make them longer. These are our electric field lines, E. And over here as well, the same. Uniform electric field. We will introduce that system tomorrow, right, in our lecture. Okay, let me emphasize that this is uniform electric field. Right? And the expression for the electric field, E equals eta divided by 2 epsilon naught. Okay, let me put an absolute value on eta. Right? Because again, this is just the strength of the electric field. Right? So this formula we will introduce again tomorrow in tomorrow's lecture. Right? Okay, so that's the first part of the system. Now the second part, let's take I think it's a proton. Yeah, a proton. So we will take a proton. So then we have a, no. Let me write it here. Then second part, we have a proton. Right. So maybe it's over here. So let's say charge Q, a proton, and it is shot away from the plate. Because if you don't shoot it, right, it will stay here because it will be attracted to the negatively charged surface, right? So let's assume that we shot it this way with initial velocity v naught. V naught is given. V naught is v sub 0 equals 2 times 10 to the power of 6. Large velocity, meters per second. And so let's first discuss conceptually what is going to happen to this proton. Of course, it is attracted to the negatively charged surface. So the force will be that way. And if you shoot it that way, so it will travel that way, decelerating, right? Because the force is in the opposite direction. So it will travel for some distance, then stops for a moment, turns around, and start moving back to the negatively charged surface. So effectively, the trajectory will be like this. Right. And this is at this point, what will be the velocity? 0. Physics 1, right? It's a turning point. It stops for a moment, turns around, and start moving in the opposite direction. So over here, velocity, of course, will be 0, right? Okay, so what do we need to find? I think we need to find this distance traveled by electron to the turning point. Okay, so now let me introduce coordinate system so that we can easily show what needs to be found. So let's say this is our x. Let me position the origin at the plate, x equals 0. And what needs to be found is over here. Oops. So x, that's what we need to find. That's our final goal. Let me check if I gave you everything. Yeah, I gave you everything. I gave you all my heart, right? Reaching the turning point, yeah. So before we start this solving problem, before we start crunching numbers, right? So I want to discuss sort of like a skeleton of the problem, right? I want to discuss in general. You know what? Effectively, it's a basically physics 1 problem. The only difference, and you solve this problem, plenty of problems like this when balls are falling down, for example, right? Or if you throw it up. It's just what's the difference between physics 1 problems and this one? It's just the nature of the force. When you drop the, I'm still looking, here, this tennis ball. If you drop it in physics 1, right, it moves under the influence of the force, under the influence of the gravitational force. Here, proton moves under the influence of the electric force. That's the only difference. Nature of the force. Otherwise, it's a physics 1 problem. Again, just the nature of the force, nature of forces are different. Right? Okay, so now we're going to use plenty of stuff from physics 1. So it's a good mixture of physics 1 and physics 2. Okay, so now let me create a skeleton of this problem, right? Discuss all major steps that we will have to make. And I will start from the very end. So what we need to find at the end, we need to find x, right? So that's our end. And what should be the point before that? So basically x, what is x? It's one of the kinematic parameters. Again, it's a physics 1. You remember in physics 1, we had sort of like 3 layers of kinematic parameters. The first, the top one, position, distance, displacement. Then you differentiate these quantities in order to get to the next level, deeper. Velocity, average velocity, right? So all this on that level. And then if you differentiate that velocities, you can get to the acceleration level, the deepest level, right? So 3 sets of parameters, positions, velocities, accelerations, 3 levels, and then of course time. So basically that's the kingdom of kinematics, which consists of these 4 sets of quantities. Again, as I said, position, velocity, acceleration, and time. Right? So we need to find one of those guys. And every time, what did we use in order to mess up, in order to calculate something in the world of kinematics? Most of the time, we used kinematic equations. So we will have to use kinematic equation to find this x. So let me write. So we will have to use kinematic, equations. So we will have to use kinematic equations. And every time one of the major quantities in the kinematic equations, and every time we used it, acceleration. So the step before this, so we will have to find acceleration. So if you know acceleration, you can use kinematic equations with some initial conditions, right? You should be able to find position. Now, the previous step, before acceleration, so how can we find acceleration? Usually, we use Newton's second law. So if you know force, you should be able to get acceleration. So using Newton's second law. So I'm just outlining the skeleton of the problem. So all major points. And of course, the nature of the force will be electric force, Fe. And then how can we find electric force if the electric field is given? Yeah, we need to know the electric field. So electric field, and then using the formula which we introduced today, F equals QE, you can find from the electric field, you can find electric force, then acceleration, and then position. In your homework, you will have to find something that I don't remember at the end, but the structure will be very similar. So that's basically the skeleton of the problem. So now let's get through the steps. Right? And now, of course, we will start from the beginning. Right? So we need to first write down the electric field, then force, acceleration, and then position. So let's start with the electric field. Electric field created by this. So we know the expression for the electric field. Let me write it in a vector form, because here directions are kind of important, so let me write in a vector form. So, and this is the expression. So electric field equals absolute value of the surface charge density divided by 2 epsilon naught. And now let's look at the picture and write it as a vector. You see, electric field points that way, because the charge, the Q, the proton, is on this side of the plate, so electric field points that way, which is the negative x direction. So in the vector form, I will have to put minus I hat. Right? So that's the expression for the electric field in the vector form. And again, you can say, but how about electric field over here? Yeah, electric field over there points this way, but our proton is on this side of the plate, where the electric field points that way. Right? So that's why I put minus I hat. I hat unit vector showing the positive direction of the x-axis. So we are here, electric field. Now, using this formula, we should be able to find the electric force. Right? So electric force, Fe, will be, we just need to take charge of the proton times this, Q times E. So it will be the whole thing multiplied by Q. Q times eta divided by 2 epsilon naught, and in minus I hat direction. Does it, let's just check, does it make sense? You see force, this is force. Does it make sense that our force points in the negative x direction? Because all this is positive, points in the negative x direction. Yeah, it makes sense, look, because this proton is attracted. Proton is a positively charged object, a plate is a negatively charged object, positive and negative, they are attracted. So of course, as proton flies, the force will be that way. I can even probably show the direction of the force, right? So the force, of course, will be this way, towards the plate. Yeah, so it means, yeah, it works, it's correct. So the force that way. So now we have to move to this acceleration point. So we just need to take this and divide it by mass. So Newton's second law. Okay, so now acceleration will be equal electric force divided by the mass, Newton's second law. Right? So just basically the whole thing divided by m. So it will be Q times eta divided by 2 m epsilon naught, and still acceleration, of course, in the negative x direction. Again, it makes sense because as proton travels, it is decelerating, right? Decelerating, and eventually it stops for a moment, turns around, and moves back. Right? So this is a turning point. So that's acceleration, and acceleration is negative. So that's what we need, and that's why I kept writing in a vector form. All right, so now let's finish this problem. So acceleration is negative, so we need to remember. And now which kinematic equations to use? Kinematic equation. No, first of all, can we use kinematic equation? Is it legal to use kinematic equations over here? What's the test that we have to run in order to convince ourselves that kinematic equations is legal to use? Acceleration must be constant. All kinematic equations were derived for the case when acceleration was constant. So I can write it so. Since A is constant, so we can use kinematic equations. Kinematic equations can be used. Okay, so which one? There are three of them. You remember the first one, velocity, which allows us to predict velocity of the system in the future, right? V equals V naught plus AT. We don't know the travel time. So that equation is good. We know the final velocity, right? But the travel time is not known. Of course, you can get it from other equation, but that will be more complicated. Then, position, equation for x. Equation for x, the same problem. In the equation for x, x equals x naught plus v naught t plus a t squared over 2. Again, time is involved. And in our problem, we don't have a single piece of, we don't have any information about time. So basically, of course, those equations can be used, but then we somehow need to find time and then use those kinematic equations. So it's not the best, it's not the simplest approach. But we have an equation number 3, which was derived for the cases where information about the time is not given, and the question is not about finding time. That's the beauty and the reason why the equation number 3 was derived, which I usually call a no time equation. So let's use just equation number 3, right? So which is v squared equals v naught squared plus 2a x minus x initial. That's no time equation. Okay, let me write it. So it's I call it usually a no time equation. Oops, no time equation, because that's the major feature of this equation, that the time is absent. Okay, and now let's see. Final velocity, 0. Then, initial position. The proton starts from the origin, so initial position also 0. Acceleration is negative, we know, we found it. Initial velocity is given, so, and this is our unknown. Okay, so basically one equation, one unknown problem is basically solved. Now we just need to solve it for x. Right. So let me move. So it will be 2ax equals to minus v naught squared. I just move v naught squared to the other side of the equation. And of course, we need to find what? We need to find x. So let's solve it for x. X will be equals to minus v naught squared over 2a. And you shouldn't panic about the negative sign. Acceleration is negative. Right. And we cannot drop that, right? So we need to keep track of the sign of acceleration in these kinematic equations, right? If acceleration negative, we need to bring that minus into the equation. You remember physics 1, right? Of course. All right, so will be minus v naught squared divided by 2, and let me rewrite it with minus, of course, q eta divided by 2m epsilon naught. Because now I dropped the unit vector sign because I need it only to get that minus. And now in the kinematic equations are not a vector equation. Right, so what 2 can be cancelled, right? And that's the answer. So it will be v naught squared. This m epsilon naught goes to the numerator and divided by q and absolute value of the surface charge density. Right? Okay, so if you put all the numbers, of course I'm not going to do it, charge of the proton, it's like charge of an electron, but positive. A mass of the proton, open the book, right, and you can see that on the cover, on the front cover, I think on the back side. So x equals to 0.18 meters. So that's the value, I mean that's the distance the proton travels with this velocity if you shoot it from the negatively charged surface. So it's 18 centimeters, actually it's something like this, right? It's a decent distance. Okay, there was another conceptual question which I thought about discussing, but it's not that crucial.